Soft robots are flexible, compliant, and predominantly made of elastic materials. They have a very high number of degrees of freedom, and this makes it difficult to sense the deformation of their bodies. Ideally, there should be many tiny sensors embedded in the soft material, but this would require a complex and expensive manufacturing technique. In this work, our goal was to create a new method for sensing the deformation of soft robots using a small number of cheap sensors. Our idea is based on the observation that the brain integrates proprioceptive sensoring from inside of the body and attached to the muscles, and exteroceptive sensoring, such as the sense of vision. This is the reason, for example, why we can imagine what our body looks like even if our eyes are closed. We use this observation to create a new method for sensing the nonlinear deformation of soft bodies. We put 4 resistive bend sensors in an octopus-inspired soft arm, and we use these as proprioceptive sensors. Furthermore, we used a camera as exteroceptive sensor in order to capture the nonlinear motion of the soft arm. Our goal was to integrate these 2 types of sensors. First, we recorded bend and camera data while the arm was in motion. The arm was placed in a tank filled with water, and the top was moved horizontally. Both the data received from bend sensors and the video frames needed to be pre-processed. We used a low-pass filter in order to reduce the noise of the signal of the bend sensors, and the images were transformed using blur, grayscale, and threshold operations. After that, we used a recurrent neural network in order to map the temporal signal of the bend sensors to the frames of the video. We used the data received from the bend sensors as input and the video frames as output. However, in this case, the number of neurons on the output layer was 3 orders of magnitude higher than on the input layer, and the recurrent neural network was underfit. Therefore, we used a stacked convolutional autoencoder in order to create a set of low-dimensional features to represent the video frames. And in the final configuration, these features and the bend sensors data were used to train the recurrent neural network. Finally, the trained decoder component was connected to the recurrent neural network, creating a path for the information to flow from the bend sensors to the visual output. As a result, the soft robot can learn to estimate and therefore to imagine its motion, even when its visual sensor is not available. Our results are shown on this slide. On the left-hand side, you can see the original and predicted temporal signal of the encoded features, and on the right-hand side, we show the original and predicted shape of the body. The proposed method has the potential to be used to sense the shape of soft robotic bodily awareness and to improve the efficiency of soft robots in all kinds of tasks in which the body is involved. If you'd like to know more about this work, come and find me during the poster session.